All right, let's talk about forward feature selection, the secret weapon for building lean, mean, high-performance machine learning models. Instead of throwing every possible feature into the mix, we take a smarter approach. Start with nothing and add one feature at a time, carefully testing which ones actually improve the model. It's like assembling a dream team. Only the best make the cut. First, we'll break down why feature selection is so important and explore different methods to trim down datasets while boosting accuracy. Then we'll walk through the step-by-step process of forward feature selection, from evaluating features to making the final selection. But no technique is perfect, so we'll also cover the pros, the cons, and how to dodge common pitfalls like overfitting, wasted computation, and hidden biases. Of course, this isn't just theory. We'll see how it works in real-world applications like marketing, healthcare, and finance. We'll compare forward versus backward selection, look at the best tools like sklearn and stats models, and even dive into Python and R code to bring it to life. Then we tackle the big questions. How do you measure if feature selection is working? What happens when your dataset gets huge? How does this technique fit into Ensemble's time series and deep learning? And most importantly, how do you keep your models transparent and fair? Finally, we'll explore the future of feature selection, including automated techniques and optimization strategies that are making models smarter than ever. Whether you're refining your machine learning skills or just starting out, this will change how you build models. Stick around, this is going to be good. So you're building a machine learning model and you've got a ton of data. Naturally, you want the best results, so you throw in every feature imaginable because more data means a smarter model, right? Wrong. What you've just created is a bloated, overcomplicated monster that's about as useful as a GPS that suggests every possible route at the same time. Your model doesn't know what's important and what's just noise, and now it's struggling to make sense of it all. Enter forward feature selection, the Marie Kondo of machine learning. Instead of dumping everything into the mix and hoping for the best, this method starts with nothing and carefully adds features one by one, testing each to see if it actually improves performance. It's like assembling an all-star basketball team where you only draft players who truly make a difference. No dead weight, no distractions, just a lean, efficient, high-performance model. But here's the catch. Forward feature selection isn't just about picking features, it's about strategy. Do it right and your model will be faster, smarter, and easier to interpret. Do it wrong and you could waste hours training a model that still doesn't perform well. So in this video, we're diving deep into how it works, why it's so powerful, and how to use it like a pro. Plus, we'll bust some myths, avoid common mistakes, and even look at real-world applications that prove why this method is a game changer. By the time we're done, you'll not only understand forward feature selection, you'll know how to use it to make your models better, faster, and more reliable. Ready to master this skill? Let's get into it. Let's take a step back for a second. What even is feature selection, and why should you care? Imagine you're packing for a trip. You could shove everything you own into a suitcase, just in case you might need it. But then, surprise, you're hit with overweight baggage fees, and now you're dragging around stuff you'll never use. That's exactly what happens when you dump too many features into a machine learning model. Feature selection is the process of picking only the most relevant features, the ones that actually improve your model's performance. It helps cut down the noise, reduce overfitting, and make your model faster and more interpretable. There are a few different ways to do this: filter methods, wrapper methods, and embedded methods, but today we're zeroing in on one of the most effective: forward feature selection. This isn't just about making your model work, it's about making it work better. The fewer unnecessary features you have, the more efficient and accurate your predictions become. So before we start adding features one by one, let's get a solid grip on why this matters and how different methods approach it. Because, trust me, once you start using feature selection properly, your models will never be the same again. You ever see someone at the gym using every single machine without a plan? 1 minute they're on the treadmill, the next they're lifting weights, then suddenly they're doing yoga in the corner. They're working hard, but are they working smart? That's exactly what happens when you build a machine learning model without a structured feature selection process. You throw in every variable you can find, thinking more data means better results, but in reality, you're just exhausting your model with unnecessary complexity. Forward feature selection changes the game. Instead of overwhelming your model with every possible feature, we take a more calculated approach. We start with nothing, just a blank slate. Then, one by one, we test and add features, only keeping the ones that actually improve performance. It's like assembling a dream team. You don't just let everyone in, you test their skills, see how they contribute, and only keep the ones that really make a difference. Now, this isn't some random guessing game. It's an iterative process that follows a clear strategy. First, we build a simple baseline model, our before picture. Then we systematically test each potential feature, measuring how much it improves the model. If it boosts accuracy or reduces error, it stays. If it doesn't, gone. We keep going until adding new features stops being beneficial. The end result? A lean, efficient, high-performance model that isn't weighed down by useless data. Think of it like cooking. You start with a basic recipe and add ingredients one by one, tasting as you go. Salt? Good. Garlic? Even better. Mustard and chocolate syrup? Maybe not. The goal isn't just to add more, it's to add better. Forward feature selection does the same thing for machine learning, ensuring that every feature in your model is there for a reason. And trust me, once you start using this technique, you'll never go back to the throw everything in and pray method again. Let's break down exactly how this works. If forward feature selection were a superhero, its superpower would be making your machine learning model smarter with less. And in a world where more data is often mistaken for better data, that's a game changer. So, why do we love this method? Simple. It makes models more accurate, prevents overfitting, and keeps everything easy to interpret. Kind of like cleaning out your closet and realizing you only ever needed 5 good outfits in the first place. First up, model accuracy. When you only keep the most relevant features, your model isn't distracted by useless noise. It's like asking a detective to solve a case, but only giving them the important clues instead of dumping an entire library of unrelated documents on their desk. With fewer but stronger features, your model learns faster, generalizes better, and predicts more accurately. Then, there's the overfitting problem. Imagine training for a marathon by memorizing every crack in the pavement on your practice route. Sure, you might run that specific path flawlessly, but the moment the race moves to a different road, you're lost. Overfitting happens when your model memorizes your training data too well, learning the noise instead of the real patterns. Forward feature selection reduces that risk by keeping only the most meaningful variables, helping your model focus on the actual signals rather than random quirks in the dataset. And let's not forget interpretability. Ever worked with a model that spits out predictions but leaves you scratching your head, wondering why? A bloated model with hundreds of variables is nearly impossible to explain. But a model with a streamlined set of features? Now we're talking. When stakeholders ask, why did the model make this decision? You'll actually have an answer. And trust me, that's the difference between building a model people trust and building one they ignore. So better accuracy, less overfitting, and clearer interpretations sounds pretty solid, right? But before we get too excited, let's talk about the flip side. Because while forward feature selection is powerful, It's not perfect, and if you're not careful, you could run into some serious pitfalls. Let's get into that next. Forward feature selection might sound like the holy grail of model optimization, but let's not get ahead of ourselves, because just like eating too much cake, there is a downside. And if you're not careful, this method can turn from a performance booster into a slow, computationally expensive nightmare. So, before you go all in, let's talk about the not so fun parts of forward feature selection. First, let's talk about the brutal amount of computation. Every time you add a feature, the model needs to be trained and evaluated again. And again, and again. This means if you've got 100 features, you're looking at potentially hundreds of models being trained just to find the right combination. If your dataset is big, congratulations. You've just signed up for an all-you-can-eat buffet of processing time. Your computer might actually hate you for this. Then there's the suboptimal feature selection problem. Because forward feature selection builds the model one feature at a time, it doesn't always make the best long-term choices. Think of it like assembling a soccer team by picking players one at a time based on their individual stats, without considering how well they play together. Sometimes the best features work in combination, and this method isn't always great at catching those subtle interactions. And let's not forget about limited scalability. The more features you have, the longer this process takes, exponentially. Forward. Feature selection is great when you're working with a handful of features, but if you're dealing with thousands, this method becomes impractical. It's like choosing ingredients for a recipe by taste testing every single possible combination. Sure, you'll find the perfect mix eventually, but at what cost? Finally, time consumption. If you're under pressure to get results fast, forward feature selection might not be your best friend. It's slower than other techniques like LASSO or embedded methods that can shrink feature sets in one go. Forward selection is meticulous, which is great for precision, but not so great when you're on a deadline. So, is it a bad method? Absolutely not. It's just not always the right tool for the job. And before you commit, you should know there's another approach, the complete opposite actually, called backward feature selection. Instead of starting from scratch, it begins with everything and removes features one by one. Which one's better? Well, let's find out. Imagine you're decluttering your closet. Forward feature selection is like starting with an empty rack and carefully adding only the best pieces one by one. But what if you took the opposite approach? What if you started with everything and methodically removed the pieces that don't belong? That's backward feature selection. Instead of building up from nothing, it begins with all features and eliminates the least useful ones one at a time until only the most impactful remain. So, which approach is better? Well, it depends. Forward selection is great when you have a massive dataset and want to quickly identify the most important features without overwhelming your model. Is like drafting a sports team from scratch. You're only picking the best players as you go. On the other hand, backward selection is perfect when you're working with a smaller set of features and want to make sure you're not accidentally removing something valuable. Think of it as editing a novel. You start with everything and cut out the fluff until only the best parts remain. But there's a catch. Backward selection requires training models with all features first, which can be computationally expensive, especially with large data sets. If you've got thousands of features, this method will chew through processing power like a kid in a candy store. Meanwhile, forward selection is more efficient because it only deals with a few features at a time, but it can sometimes miss feature interactions that would only be obvious in a larger set. So, no clear winner here. It all comes down to the situation. If you have a huge data set and need speed and efficiency, forward selection is your best bet. If you've got a manageable number of features and want to be extra thorough, backward selection might be the way to go. And if you really want to get fancy, some hybrid methods combine the best of both worlds. Now that we know how forward selection stacks up against its closest competitor, let's talk about real-world applications. Because in theory, all of this sounds great, but how do people actually use forward feature selection in the real world? Let's get into it. Data science isn't just about algorithms and models, it's about solving real problems. And forward feature selection? It's not just some theoretical trick. It's actively shaping industries, making predictions more accurate, and helping businesses make smarter decisions. Let's take a look at how this method is being used in the real world. First up, marketing. Ever wonder how companies seem to know exactly what ad to show you? It's not magic, it's machine learning. Forward feature selection helps marketers identify the most important factors that drive customer behavior. Instead of wasting time analyzing every possible data point, they focus on the key predictors, like browsing history, purchase frequency, or even the time of day you shop online. The result? Highly targeted campaigns that actually work instead of just throwing ads at people and hoping something sticks. Then there's healthcare, where the stakes are much higher. Imagine you're trying to predict whether a patient will develop a certain disease. You've got a massive data set, everything from medical history to genetic information to lifestyle habits. Instead of feeding the model every possible feature and hoping for the best, forward feature selection picks out the most relevant indicators, improving prediction accuracy while keeping the model interpretable. This not only helps doctors make better decisions, but also prevents AI from making mysterious black box predictions that no one can explain. And let's not forget finance. In the world of stock market predictions and credit scoring, having the right features in your model can mean the difference between making money and losing it. Forward feature selection helps analysts identify which financial indicators, interest rates, inflation, historical trends, are actually useful in predicting stock performance or assessing credit risk. No more drowning in endless economic variables, just the ones that actually matter. So whether it's optimizing marketing campaigns, improving medical diagnoses, or making better financial predictions, forward feature selection is out there making real-world impact. But what does it actually look like in action? Let's go even deeper with a case study from the healthcare industry and see exactly how this method has been used to improve patient outcomes. Predicting patient outcomes is one of the toughest challenges in healthcare. With so many factors at play, age, genetics, medical history, lifestyle habits, it's easy to get lost in a sea of data. Doctors and researchers need models that don't just spit out predictions, but actually help them understand why certain patients are at risk. And that's exactly where forward feature selection steps in. In a real-world case study, researchers wanted to develop a model to predict patient recovery times after surgery. They had a massive data set filled with hundreds of potential features: blood pressure, pre-existing conditions, medication history, diet, exercise habits, you name it. But not all of these variables were equally important. Instead of overloading the model with noise, they used forward feature selection to identify the most relevant predictors, ones that had a significant impact on recovery speed. The results? A much simpler, more accurate model. Instead of relying on a bloated algorithm that required tons of data and computing power, the refined model focused on a small set of high-impact features. Things like post-op inflammation levels, specific medications, and early mobility scores. Not only did this improve accuracy, but it made the model interpretable. Doctors could now see which factors were driving patient outcomes, allowing them to tailor treatments more effectively. And here's the real kicker. This method didn't just improve predictions, it improved actual healthcare decisions. Hospitals use these insights to adjust patient care plans, speeding up recovery times, and reducing complications. That's the power of feature selection. It's not just about making models run faster, it's about making them smarter and more useful. But how do we measure whether forward feature selection is really working? What makes one feature set better than another? That's where performance metrics come in. Let's break down how we evaluate the success of feature selection. So, how do we know if forward feature selection is actually doing its job? Sure, we've picked a set of features, but how do we measure whether they're better than the rest? This is where performance metrics come into play, the stats that separate a good feature selection process from a bad one. First up, accuracy. It's the simplest metric. How often is the model correct? Sounds great, right? Well, not always. If you're working with imbalanced data, like fraud detection, where 99% of transactions are legit, a model could be 99% accurate just by predicting not fraud every time. So while accuracy is useful, it doesn't always tell the whole story. That's where precision and recall come in. Precision answers the question, when my model says something is important, how often is it actually correct? It's great for situations where false positives are a big deal, like predicting cancer. You don't want a model freaking out over every minor symptom. On the flip side, recall measures how many of the actual important cases your model caught. If you're screening for a rare disease, you want high recall, you'd rather flag too many cases than miss a critical one. And then there's the F1 score, the best of both worlds. It balances precision and recall to give you a more complete picture of how well your model is performing. A high F1 score means your model is both catching important cases and minimizing false alarms. Finally, we've got feature importance. Some models, like decision trees and random forests, can tell you which features actually contributed the most to predictions. If forward feature selection worked well, the most important features should match the ones we selected. If not, we might have left something important out or kept something we didn't need. Feature selection isn't just about making the model simpler. It's about making sure it actually performs better. And if the numbers don't back it up, we go back to the drawing board. But what about mistakes? Even with the best metrics, there are still some common pitfalls that can trip you up. Let's talk about what not to do next. Feature selection is like trying to pack for a trip with strict baggage limits. You've got to choose wisely. But even with the best intentions, people make mistakes. And in machine learning, those mistakes can cost you accuracy, generalization, and even the trustworthiness of your model. Let's go over some of the biggest pitfalls in forward feature selection so you don't fall into them. First up, ignoring domain knowledge. Just because a feature looks statistically significant doesn't mean it actually makes sense in the real world. Imagine a healthcare model that prioritizes a patient's shoe size as a top predictor for heart disease. Sure, the numbers might show some correlation, maybe taller people have different risk factors, but does it actually mean anything? If you don't loop in domain experts, whether doctors, financial analysts, or engineers, you risk building a model that's technically correct but practically useless. Then there's the validation problem. Some people get so caught up in fine-tuning their features that they forget to properly validate the model. Overfitting is a sneaky beast. It tricks you into thinking your model is performing well when in reality it just memorized the training data. Cross-validation is your best friend here. Skipping it is like studying only the exact questions from last year's exam and expecting to ace a brand new test. Spoiler, it won't work. Next, we've got feature redundancy. Ever added two features that basically say the same thing? Think about using both temperature in Fahrenheit and temperature in Celsius in a weather model. One isn't giving you any new information. If your selected features are highly correlated, they're just taking up space and adding noise. That's why checking for redundancy using correlation analysis is key. And then there's data leakage, the ultimate silent killer of model performance. This happens when information from the future sneaks into the training data, making your model unrealistically good. A classic example, training a loan approval model with a feature like, was the loan paid back? Yeah, of course, that's a great predictor because it already knows the outcome. Models that suffer from data leakage, perform amazingly well in training, and then completely collapse when used in the real world. So those are the landmines. Ignore them at your own risk. But now that we know what not to do, let's talk about what tools we can actually use to implement forward feature selection properly. Up next, the best libraries and frameworks for getting this done efficiently. Building a great machine learning model is one thing. Actually implementing it is another. You don't want to reinvent the wheel and manually test every feature. That's where libraries and tools come in, making forward feature selection faster, smarter, and way less painful. Let's break down the best ones for the job. First up, sklearn. If you've done anything in Python machine learning, you've probably used this library. It comes with built-in tools for feature selection, including sequential feature selector, which automates forward feature selection. You just plug in your model and it iterates through your features one by one, finding the best combination. Simple, powerful, and widely used, kind of like the Swiss Army knife of machine learning. Then there's stats models, the go-to for statistical analysis. If you're working with regression models and need in-depth insights on which features are statistically significant, this is your tool. Unlike sklearn, which is focused on pure performance, stats models gives you p-values, confidence intervals, and other juicy details that help explain why a feature was selected. Perfect for researchers, economists, and anyone who wants to dig deeper into the numbers. For those working with big data, there's MMLib from Apache Spark. This one is built for speed, using distributed computing to handle massive datasets efficiently. If you're selecting features on millions of rows and thousands of columns, MLib is your best friend. It keeps things scalable so your laptop doesn't burst into flames. And if you're in R, the mass package and its step AIC function let you perform forward feature selection based on the Akaike Information Criterion, AIC, which helps balance model fit and complexity. It's a staple in statistical modeling and works great for regression-based problems. So whether you're a Python enthusiast, a stats geek, or handling big data pipelines, there's a tool out there for you. Now that we've got our toolkit, let's get hands-on. Up next, we're actually implementing forward feature selection in Python. Let's write some code. Feature selection isn't just about making a model work. It's about making it work better. And now we're putting all that theory into action with forward feature selection. No overcomplicated explanations, no unnecessary steps, just a streamlined process that gets results. Let's say we've got a dataset filled with tons of features, but not all of them are useful. Instead of feeding everything into the model and hoping for the best, we take a smarter approach. First, we separate our dataset into two parts, one for training, one for testing. Training data helps the model learn, while testing data makes sure it didn't just memorize the answers. It's the difference between studying for understanding and just cramming the night before a test. Next, we set up our model. A simple logistic regression will do, but this method works with anything, random forests, decision trees, you name it. The key is using forward feature selection to decide which features actually matter. It starts with an empty model and adds one feature at a time, testing each step to see if performance improves. If a feature helps, it stays. If it doesn't, we move on. Think of it like assembling a team. You don't just grab people at random. You pick the ones who actually bring value. But the real question is, did it work? Once we have our selected features, we retrain the model and compare its accuracy before and after. If the accuracy improves, then forward feature selection just did its job, cleaning out the noise and sharpening the model's focus. If not, maybe we need to adjust how many features we select or consider a different method altogether. No feature selection technique is perfect for every dataset, so this step is crucial. This is how we take a bloated, inefficient model and turn it into something lean, fast, and accurate. No wasted computation, no unnecessary complexity, just a model that actually makes sense. But if you're not working in Python, don't worry, this method works in R too. Let's take a look at how to implement forward feature selection using R next. Forward feature selection isn't just a Python trick. It works just as well in R. If you're more comfortable in R, or if your project is heavily statistical, this method is just as easy to implement, and it follows the same logic. Start with nothing, add one feature at a time, and keep only what actually improves the model. Simple, efficient, and powerful. First things first, you need your dataset. The setup is straightforward. Separate the features from the target variable, just like we did before. Then it's time to pick a model. Linear regression, logistic regression, whatever fits your problem. But here's where R has a special tool, Step AIC from the mass package. This function automates forward feature selection by evaluating which features should be added based on the Akaike information criterion AIC. Why AIC? Because it balances accuracy and complexity. A lower AIC score means a model that fits well without unnecessary complexity. If you only chase high accuracy, you risk overfitting. If you only focus on simplicity, you might throw away useful information. StepAIC finds the sweet spot. The process works like this. You start with an empty model, and StepAIC adds features one by one, testing each step to see if it improves the model. If adding a feature reduces the AIC, it stays. If not, it's ignored. At the end, you're left with a lean, optimized model with only the best predictors. And just like in Python, we don't just assume it worked. We test it. Once we have our selected features, we fit the final model and compare performance. If it's better than before, we've done our job right. If not, it might be time to tweak our approach or test a different selection method. So whether you're working in Python or R, the process remains the same. Start with nothing, add features one by one, keep what matters, and test your results. Now that we've built our models, how do we know if they're actually performing well? That's where validation and performance evaluation come in. Let's break that down next. Building a model is one thing. Knowing whether it actually works is another. You wouldn't buy a car without test driving it, and you definitely shouldn't trust a machine learning model without putting it through validation. So now that we've selected our features, it's time to evaluate whether they actually improve performance. First up, accuracy. It's the easiest metric to understand. It tells us what percentage of predictions were correct. But here's the problem. Accuracy alone can be misleading, especially if the dataset is imbalanced. If you're predicting fraud and only 1% of transactions are fraudulent, a model that just predicts not fraud every time will still be 99% accurate, but completely useless. That's why we need more than just accuracy, ENTA, precision, and recall. Precision tells us when the model makes a positive prediction, how often is it actually correct? It's super important in cases where false positives are a problem, like predicting diseases. You don't want a model that scares people for no reason. On the other hand, recall asks, of all the actual positive cases, how many did the model find? If you're screening for a rare disease, you'd rather have a few extra false alarms than miss actual patients who need treatment. For a balanced view, we look at the F1 score, which combines precision and recall into a single number. A high F1 score means the model isn't just getting things right, it's doing so consistently. And if you're dealing with regression instead of classification, you'll want to check metrics like RMSE, root mean squared error, to see how far off your predictions are on average. Finally, we need cross-validation. Instead of testing the model on a single dataset split, we divide the data into multiple parts, training and testing on different subsets. This makes sure the model isn't just memorizing a specific dataset, it's actually generalizing to new data. If a model performs well on one test set but fails on another, we've got a problem. Bottom line, a model with well-selected features should improve across multiple metrics, not just one. If accuracy goes up but recall drops significantly, or if precision improves but overall error increases, we might need to tweak our selection process. Feature selection isn't just about choosing features, it's about choosing them wisely. Now that we know how to measure success, let's take it one step further, understanding why certain features are more important than others. That's where feature importance analysis comes in, and it's what we're covering next. Not all features are created equal. Some are game changers, making your model significantly better, while others are just dead weight, adding noise without contributing anything useful. That's why understanding feature importance is crucial, because even after forward feature selection, we need to know why certain features were chosen and how much they actually matter. There are a few ways to measure feature importance depending on the type of model you're using. One of the most common methods is coefficient analysis for linear models. If you're using regression, the model's coefficients can tell you which features have the most impact on predictions. A high coefficient means a feature is strongly influencing the outcome, but be careful because coefficients only tell direction and magnitude, not necessarily importance relative to other features. For more complex models, we use techniques like Gini importance, used in decision trees and random forests, or permutation importance, which measures how much a model's performance drops when a specific feature is randomly shuffled. If scrambling a feature drastically reduces accuracy, it's probably important. If accuracy barely changes, that feature was just along for the ride. And then there's SHAP values, one of the most powerful and interpretable ways to analyze feature importance. SHAP, Shapley additive explanations, doesn't just rank features, it shows how much each feature contributes to a specific prediction. Instead of saying age is important, SHAP tells you, in this prediction, age increased the probability by 12%. This level of detail is a game changer for model interpretability, especially when explaining results to stakeholders. So why does this matter? Because blindly trusting a model without understanding why it works is a dangerous game. If a model performs well but relies on irrelevant or biased features, it could fail catastrophically in real-world scenarios. Feature importance helps us verify that the model is making decisions for the right reasons. But what if our features aren't just redundant, but actually interfering with each other? That's when we run into multicollinearity, and if we don't handle it properly, it can completely throw off our model. Let's break that down next. Sometimes features don't just add noise, they actively interfere with each other, causing chaos in your model. This is called multicollinearity, and if you don't handle it properly, your model's predictions could be way off, even if forward feature selection picked what seemed like the best features. Multicollinearity happens when two or more predictor variables are highly correlated, meaning they carry the same information. Think of it like having two GPS apps open at the same time, both giving you directions. Instead of making things clearer, they just confuse you. The model struggles to determine which feature is actually driving the prediction, leading to unstable results. So how do we spot it? One of the best tools is the variance inflation factor, VIF. If a feature has a high VIF score, it means that feature is strongly correlated with another one, and we probably don't need both. Another quick check is looking at correlation matrices. If two features are nearly identical, one of them can go. But what if both correlated features seem useful? Instead of just deleting one, we can try combining them into a single variable. Principal component analysis, PCA, is a popular method for this. It transforms correlated features into a new set of independent features, preserving the most important information while reducing redundancy. Regularization techniques like ridge regression can also help by reducing the impact of correlated features, preventing any single one from dominating the model. Instead of removing features, ridge assigns smaller weights to highly correlated ones, balancing their influence. Ignoring multicollinearity can lead to misleading insights, overfitting, and even instability in your model. The predictions might look good on paper, but small changes in the data can cause wild fluctuations in results. The key is to test for it early and handle it before it messes with your final model. Now that we know how to manage feature relationships, let's take things up a notch. What happens when you're dealing with massive datasets where thousands of features need to be evaluated? Forward feature selection can get tricky at scale, so let's talk about how to handle it efficiently in high-dimensional data. When you're working with just a handful of features, forward feature selection is straightforward. But what happens when your dataset has thousands of features? Things get messy fast. High-dimensional data is a whole different beast, and if you don't handle it properly, your model will be stuck crunching numbers forever, or worse, learning patterns that don't actually exist. The first problem is computational cost. Forward feature selection already takes time because it tests features one by one. Now imagine doing that for thousands of variables. It's like trying to read an entire library book by book instead of just picking the ones that matter. The more features you have, the longer this process takes, sometimes to the point where it becomes completely impractical. So how do we speed things up? One way is to pre-filter features before running forward feature selection. Techniques like mutual information, statistical tests, or even simple correlation checks can help eliminate obviously useless features before we even start. This way, instead of testing thousands of features, we only evaluate the ones that actually have potential. Another option is dimensionality reduction. Instead of selecting individual features, we transform them into a smaller set of variables that still capture most of the information. Principal component analysis, PCA, is a popular method. It condenses many correlated features into a few uncorrelated ones, reducing the dataset's complexity while preserving its structure. Think of it as compressing a huge image file without losing important details. And then there's greedy optimization. Instead of testing every single feature, we use approximate search methods to quickly zero in on the most important ones. Algorithms like genetic algorithms, random feature selection, or even neural network-based selection methods can help navigate huge feature spaces much faster than traditional forward selection. The goal isn't just to make the model run faster, it's to prevent it from overfitting to noise. High-dimensional datasets are full of irrelevant patterns, and if we don't filter them out, our model will start learning things that don't actually matter. By using smarter selection techniques, we make sure our model is only learning from useful data, not just memorizing random fluctuations. So now we know how to handle massive data sets, but how does forward feature selection compare to other selection techniques? Let's put it head to head against some of the most popular alternatives like LASSO and ridge regression to see when it's the best choice and when it's not. Forward feature selection is powerful, but it's not the only player in the game. Other feature selection methods like LASSO and ridge regression take a completely different approach, and in some cases, they might actually work better. So how does forward selection stack up against the competition? First, let's compare it to LASSO regression. LASSO, least absolute shrinkage and selection operator, is like an aggressive minimalist. It not only selects features, but also forces some of their coefficients to exactly zero, meaning they get removed automatically. Instead of testing one feature at a time like forward selection, LASSO applies a penalty to the model that encourages simplicity. The advantage? It's much faster and works well when you have a ton of features. The downside? It assumes all feature relationships are linear. So if your data has complex interactions, LASSO might miss them. Then there's ridge regression, which is similar to LASSO but never fully removes features. Instead, it shrinks the coefficients of less important features closer to zero, rather than eliminating them completely. This helps in cases where features are correlated, something that forward selection and LASSO struggle with. Ridge is great for preventing overfitting, but it doesn't actually select features, so if your goal is to reduce dimensionality, it won't help as much. And what about embedded methods? These are techniques built directly into machine learning models, like decision trees and random forests. These models can rank feature importance automatically, making feature selection part of the training process itself. The advantage? No need for a separate selection step, it's all baked in. The trade-off? These methods can be biased towards certain types of data, and they don't always guarantee the best feature subset. So when should you use forward feature selection instead of these alternatives? It's ideal when you have a moderate number of features and need an interpretable model. It's also great when your dataset has complex interactions that simpler techniques like LASSO might miss. But if you're dealing with thousands of features, or if you need a selection method that works well with regularized models, LASSO, Ridge, or embedded methods might be the better choice. At the end of the day, no method is perfect. It all depends on your data set and your goal. But once you've selected the best features, how do you make sure the model remains interpretable? Let's explore how forward feature selection improves model transparency and helps stakeholders understand what's really driving predictions. A machine learning model is only useful if people trust it. And let's be real. No one likes a black box model that spits out predictions without any explanation. That's why forward feature selection isn't just about improving accuracy, it's about making models interpretable. Because if you can't explain why your model made a decision, good luck convincing anyone to use it. By selecting only the most important features, forward feature selection naturally simplifies models, making it easier to see which factors are actually influencing predictions. Instead of a model drowning in hundreds of variables, we get a lean and focused version that's much easier to analyze. This is a game changer in industries like healthcare and finance, where decision makers need to understand why an AI model recommended a specific treatment or approved a loan. Think about it like this. If a medical AI predicts that a patient has a high risk of heart disease, doctors need to know why. Was it their cholesterol levels, their age, their exercise habits? If the model was built using forward feature selection, you can actually point to the key factors driving the prediction. But if the model was trained on hundreds of unnecessary features, good luck figuring out what's really going on. The interpretability boost also makes models easier to debug. If a model is underperforming, you can quickly check whether an important feature was left out or if a misleading feature was included. This is a huge advantage over methods like deep learning, where troubleshooting is often like trying to find a needle in a haystack. And let's not forget compliance. In regulated industries like finance and healthcare, there are laws requiring companies to explain their AI decisions. If a bank denies someone a loan, they must be able to justify it. Forward feature selection helps ensure that models remain transparent and compliant, reducing legal risks and increasing trust. So, by reducing complexity and highlighting only the most important features, this method doesn't just make models better, it makes them usable. But what about more advanced models like ensembles? Can forward feature selection still help when dealing with multiple models at once? Let's dive into that next. Some models work better together, like a team of experts, each bringing their own strengths to the table. That's where ensemble methods come in. Instead of relying on a single model, ensembles combine multiple models to improve accuracy and reduce overfitting. But here's the catch. More models mean more complexity, and if you don't carefully select your features, your ensemble can become bloated, slow, and hard to interpret. That's where forward feature selection can make a huge difference. Take random forests, for example. This model works by training multiple decision trees on different parts of the data and averaging their predictions. It's great for handling large data sets, but it can also get overloaded with too many features. Forward feature selection helps by reducing the number of input features while keeping only the most important ones, making the model faster and more efficient without losing predictive power. Then there's gradient boosting, used in powerful models like XGBoost and LightGBM. These models build trees sequentially, correcting the mistakes of previous ones. The problem? They're sensitive to noise. If you feed them too many irrelevant features, they can easily overfit. Forward. Feature selection acts as a filter, ensuring that only meaningful variables are included, leading to a model that generalizes better on new data. And let's not forget stacking. This technique combines multiple models, logistic, regression, decision trees, neural networks, you name it, and uses another model on top to make the final decision. But stacking only works if each base model is learning something useful. If your base models are overloaded with irrelevant features, the entire ensemble suffers. Forward. Feature selection ensures that each model is working with clean, high-impact data, making the final stacked model even stronger. So, while ensemble methods are powerful, they're not immune to the problems caused by excessive or irrelevant features. Forward feature selection streamlines these models, improving efficiency, reducing overfitting, and making them easier to interpret. But what if your data isn't just large, it's sequential? Time series models come with a whole new set of challenges, and forward feature selection plays a critical role in handling them effectively. Let's explore how it works with time-dependent data next. Time series data isn't like regular data. It has structure, trends, and dependencies over time. You can't just shuffle it around like a typical dataset, and if you ignore its unique characteristics, your model will make terrible predictions. That's why forward feature selection in time series analysis needs a special approach. The biggest challenge? Temporal dependencies. In time series models, past values influence future ones. If you're predicting stock prices, tomorrow's value depends on today's, yesterday's, and so on. But which past values matter most? Should we look at data from the last day, the last week, or the last month? Forward feature selection helps answer that by systematically testing which time-based features improve the model. Then there's feature engineering. In time series, raw timestamps usually aren't enough. You need to extract meaningful patterns. Things like moving averages, lagged values, seasonal indicators, and trend variables can all be useful, but not all of them will actually help. Forward feature selection sorts through these and keeps only the ones that add real value to predictions. And let's talk about overfitting. Time series models can easily overfit if you include too many irrelevant time-based features. Imagine a weather prediction model that tries to learn based on data from every single past day. Eventually, it starts memorizing noise instead of actual trends. Forward feature selection helps by ensuring only the most predictive, time-dependent features are used, making the model more generalizable. But here's where things get tricky: data leakage. In normal feature selection, we can evaluate features based on their performance across the dataset. In time series, we have to be careful not to use future data to predict past outcomes. Forward feature selection has to be applied in a way that respects the natural flow of time, making sure no information from the future accidentally sneaks into the training process. So while forward feature selection works for time series, it requires careful handling. The benefits? A leaner, more interpretable model that captures the right time-based patterns without getting lost in unnecessary complexity. But what happens when your dataset is truly massive, like millions or billions of rows? That's when we need to talk about feature selection in big data environments, and that's coming up next. When your dataset is massive, standard feature selection methods can start to buckle under the pressure. Forward feature selection is great for picking the best features, but when you're dealing with millions or even billions of rows, testing features one by one can turn into a never-ending process. That's why in big data environments, we need smarter ways to make it work without sacrificing efficiency. The first big issue? Computational cost. Forward feature selection requires training multiple models, one for each feature added. When you have thousands of features, this quickly becomes impractical. A single selection process could take days to run. The solution? Parallel processing. Instead of testing features one at a time, we distribute the workload across multiple processors or even multiple machines. Tools like Apache Spark's MMLlib make this possible, allowing feature selection to scale across big data clusters instead of being stuck on a single machine. Another challenge is data storage and access speed. When working with big data, retrieving features from storage can become a bottleneck. Instead of working with raw datasets, feature selection in big data environments often involves feature engineering pipelines where precomputed statistics, aggregations, and transformations are stored efficiently for quick access. This minimizes the amount of redundant computation and speeds up the selection process. And let's talk about alternative selection strategies. When forward feature selection is too slow, we can use approximate methods that find good enough solutions without testing every single feature combination. Genetic algorithms, random feature sampling, and distributed search techniques can help navigate large feature spaces faster while still maintaining strong model performance. Finally, scalability. Traditional machine learning libraries like sklearn struggle with big data, but specialized frameworks like Spark MLlib, Rapids for GPU acceleration, and TensorFlow Extended (TFX) are designed to handle massive feature sets efficiently. These tools optimize feature selection to work at scale, ensuring that even in the biggest datasets, we're still able to identify the most important variables without bringing everything to a crawl. Big data requires big optimizations, but with the right approach, forward feature selection can still be a powerful tool. However, it's not just about performance, it's also about making sure feature selection is fair and doesn't introduce bias into the model. That brings us to a critical discussion: ethical considerations in feature selection. Let's dive into that next. Feature selection isn't just about improving model performance. It's also about making sure our models are fair and ethical. Because here's the thing. If we're not careful, forward feature selection can accidentally reinforce biases, introduce unfairness, or make models that favor certain groups over others. And that's a problem, especially in industries like finance, healthcare, and hiring, where AI decisions have real-world consequences. One of the biggest risks: bias in feature selection. If our dataset contains historical biases, say in loan approvals or job applications, forward feature selection might unknowingly prioritize features that reflect those biases. For example, if a hiring model selects zip code as an important feature, it might be making decisions based on socioeconomic background rather than actual qualifications. Without careful oversight, feature selection can automate discrimination instead of eliminating it. Then there's data leakage from unfair correlations. Some features might seem neutral, but actually act as proxies for sensitive information. For example, a model might not directly use race as a feature, but if it selects things like neighborhood or income level, it could still end up making racially biased predictions. This is why fairness metrics, like disparate impact and equalized odds, are critical when evaluating selected features. Transparency is another major issue. If a model is making high-stakes decisions, people deserve to know why. Forward feature selection helps by keeping models interpretable, but we still need to document which features were selected and why. In regulated industries like finance and healthcare, explainability isn't optional, it's a requirement. Companies need to show that their models are making decisions based on valid, non-discriminatory factors. So how do we make sure feature selection is fair? First, we must involve domain experts, not just data scientists. Ethical AI requires input from people who understand the real-world implications of these models. Second, we should apply fairness constraints during feature selection, actively removing features that introduce bias. And finally, we need ongoing audits, checking models after deployment to ensure they're still behaving fairly as new data comes in. Ethical AI isn't just about following rules, it's about building trust. When people know that an AI model is selecting features fairly and transparently, they're more likely to trust its decisions. And as AI continues to shape industries, this trust is going to matter more than ever. But what's next for feature selection? AI is evolving, and so are the techniques we use to optimize models. Let's take a look at the future of forward feature selection and where things are headed next. Feature selection isn't just about what works today, it's evolving just like the rest of machine learning. As data sets grow larger and models become more complex, forward feature selection is getting some serious upgrades. The future of feature selection is all about speed, automation, and deeper insights. One of the biggest trends, automated feature selection. Right now, forward feature selection still requires some manual tweaking, deciding how many features to keep, fine-tuning hyperparameters, and evaluating model performance at each step. But with advances in AutoML, automated machine learning, feature selection is becoming more hands-off. AI-driven selection methods are emerging using reinforcement learning and deep learning to dynamically find the best features without human intervention. Then there's deep learning integration. Traditional forward feature selection is mostly used in structured datasets, like tables of customer transactions or medical records. But what about unstructured data, like images, text, and audio? Neural networks are learning to apply feature selection techniques inside deep learning architectures, identifying the most relevant patterns in massive datasets while filtering out noise. Expect to see hybrid approaches that combine forward feature selection with deep learning feature extraction. Another big shift, ensemble feature selection. Instead of using just one method, researchers are combining multiple feature selection techniques to create more robust results. Some features might be selected using statistical tests, others using machine learning algorithms, and then combined into a final set. This helps balance efficiency, accuracy, and interpretability, especially for large-scale applications. And let's talk about optimization techniques. Forward feature selection is great, but it can be slow on huge datasets. The future is all about smarter, faster algorithms, things like evolutionary strategies, genetic algorithms, and Bayesian optimization. These methods allow feature selection to scale efficiently, even when working with high-dimensional data. Finally, we're seeing a push toward ethical, interpretable AI. As regulations around AI decision-making become stricter, feature selection methods will need to prioritize fairness and transparency. Expect new tools that automatically detect and remove biased features, ensuring that AI models make fair and justifiable decisions. In short, feature selection isn't going anywhere. It's just getting better, faster, more automated, and more intelligent. And if you're building machine learning models, understanding these trends will keep you ahead of the curve. So, what have we learned? Let's wrap things up with a quick summary of everything we've covered. We've covered a lot, and if there's one thing to take away, it's this. Forward feature selection isn't just a technique, it's a game changer for building smarter, faster, and more interpretable machine learning models. It helps cut through the noise, selecting only the most relevant features while improving accuracy, reducing overfitting, and making models easier to understand. We started with the basics, what feature selection is, why it matters, and how forward feature selection works step by step. Then we broke down the advantages, from boosting model performance to making predictions more interpretable. But we didn't just focus on the good stuff, we also tackled the downsides like computational cost and scalability issues and explored how to work around them. We compared forward selection to backward selection, LASSO, ridge regression, and other techniques, seeing where it shines and where other methods might be a better fit. We also looked at real-world applications, how it's used in marketing, finance, and healthcare, and even walked through a case study that proved its impact in patient outcome prediction. Then we got practical. We saw how to implement it in Python and R, discussed key performance metrics like precision, recall, and F1 score, and explored feature importance to understand why certain variables matter. From handling multicollinearity to working with high-dimensional data and ensemble models, we tackled every major challenge that comes with feature selection. And finally, we zoomed out to the big picture. We talked about ethical concerns, the need for fairness and transparency in AI, and where feature selection is headed. Automation, deep learning integration, and more efficient optimization techniques that are making machine learning models better than ever. The bottom line, forward. Feature selection is a powerful tool, but like anything in machine learning, it's not one size fits all. The key is knowing when to use it, how to implement it, and why it matters for your specific problem. Now that you have a complete understanding, it's time to put it into action. So, whether you're fine-tuning a predictive model, building an AI-driven product, or just trying to make sense of a massive data set, you now have the tools to make better data-driven decisions. The question is, what will you build next?